Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office, or NNCO. It's my pleasure to welcome Kurt Kolosinski, Professor of Chemistry at West Chester University in West Chester, Pennsylvania. His research focuses on surface science, laser surface interactions, and nanoscience with a particular expertise in the formation of nanostructures in silicon and porous silicon. He is also the author of 2 textbooks, including Surface Science, Foundations of Catalysis and Nanoscience, and more recently, Physical Chemistry, How Chemistry Works. Kurt, thank you so much for taking the time to talk with us today. Could you first tell us a little bit more about yourself and how you originally got involved in nanotechnology?
Sure. Thank you. Thank you, Lisa, for this opportunity. I'm really happy to talk about nanotechnology. I've been involved for quite some time when I think about it. When I was an undergraduate back in 1983, my very first research project was with, well, we called them colloidal gold at the time. Now you'd say gold nanoparticles. Put those on a surface, and we were essentially looking for surface-enhanced infrared spectroscopy. And we got some nice results. I was back in John Yates' lab back at the University of Pittsburgh working with Tom Beebe. He was a graduate student at the time. He's a professor at University of Delaware now. But, we got a few results. Nothing we've published, actually, but it was my first introduction to nanoparticles. Then I continued with an interest in surface chemistry. And surface chemistry is just naturally linked with the area of nanoscience, nanotechnology. One, because you're down there at that length scale where you're looking at things at atom resolve, molecular resolve. That's where we wanted to be. That's where we wanted to go. We didn't have those tools yet back then, but that's where we wanted to go. I was really interested always in getting an atomistic, mechanistic understanding of systems. And one area that things were certainly related to in the nanotechnology side was catalysis, trying to explain the reactivity of metal nanoparticles. Then another thing I started to understand was, well, one thing I understood was I was not a very good organic synthetic chemist. Making molecules wasn't really my thing, but I liked structure. As I got more involved in surface chemistry, I realized that there was this field that was developing, nanoscience, where sometimes the structure was your product. That even without changing the molecular composition of a material, just by changing its size, by changing its shape, you could change the characteristics of a material. And I found that fascinating. So that's where my interest really took off on, just trying to develop ways to make new structures and to characterize the properties of those structures.
So Kurt, immediately before we dialed in with you today, I was having a conversation with Mallory, my AAAS fellow, about free nanoparticles or nanomaterials and structure and what you can do with structuring a surface. And some of the examples that people talk about are superhydrophobic surfaces, some of the laser ablation or surface texturing for photovoltaics. But you've done a lot of surface interactions to form porous structures, like porous silicon. Can you discuss that a little bit?
So something that I find very interesting about nanoscience is that we've always got this fab side, Intel and things like that, and there's simplicity. And that's one thing I've really tried to develop in the porous materials is how can you find ways that you have self-limiting chemistry, self-limiting processes that will make the nanostructures for you so that you don't have to have a $4 billion fab. And that's where I started off with laser techniques, trying to do that, and eventually moved over to what is really electrochemistry and trying to find self-limiting electrochemical methods to form nanostructured silicon, whether that's silicon nanoparticles, silicon powders that are porous, and then maybe even making nanopores in nanoparticles. And that's been the focus of my research for the last few years, and really where I've had perhaps the greatest impact on that is developing these techniques to let the chemistry do the hard part for you, which is to select sizes and stop etching silicon when it gets to the nanoscale, rather than trying to have to position every atom by yourself through a very complex process.
Thank you for that description. I want to switch gears a little bit. As you know, the NNI is celebrating its 15-year anniversary. I just wanted to ask, could you please give us your perspective on the key research advances that have been made in nanotechnology over the past 15 years?
Well, there's three things I'd like to highlight. One from theory and two from experiment. One from theory is, as I said, I've been looking at surface chemistry, and that's tied into the chemistry of metal nanoparticles, which has historically been a black box. How do you develop better catalysts? And what theoreticians have developed over the last 15 years in particular is a way to get a much better quantitative understanding of the reactivity of metal nanoparticles. D-band theory from Jens Norskov and co-workers and many others are working on that. And the descriptor model of trying to explain chemical reactivity as a function of a parameter of a system has helped us to understand reactivity, but also predict where we should look for, what types of materials we should look at, how we should try to optimize the materials we have to improve their catalytic activity. And it's hard to underestimate just how important catalytic reactions are in the world of chemistry, where around 90–95% of all industrial chemical reactions are catalytic reactions. So that the ability to better catalyze things is really important in the chemical industry. And moving forward to find energy solutions, we're going to have to extend this understanding to electrocatalysis as well. And this D-band theory is going to be an essential part for doing that. Then on the experimental side, there are two things I'd really like to highlight. One is these 2D materials, that we could find a whole new class of matter from taking Scotch tape and exfoliating graphene layers from graphite, a material that's been around us forever, is simply stunning. And again, finding graphene, it again was a perspective-changing moment where once we had that conception, yes, you can get a graphene layer, a one-atom thick layer in a sheet that was stable, then now let's look around to other layered materials and see where else we can find 2D materials, layered materials like this. And sure enough, there were other examples. And then we can do things like take a molybdenum disulfide layer and sandwich it between boron nitride or graphene layers, and suddenly we have a new way to make devices. For the longest time in semiconductor processing, it always seemed like processors, that's where everybody was concerned about, making your processor faster and smaller critical dimensions and faster switching. Well, eventually we got switching about as fast as we could, and everybody was worried that Moore's law was going to run out, and it had essentially on switching speeds. But the march of memory continued. Memory marching on to smaller and smaller critical dimensions. And now we're even getting rid of hard drives and replacing them with a solid state device. And memory has become so cheap. And it's enabled cloud computing and things like the flash drive stick that you may have in your pocket. It's an amazing, amazing advance in nanotechnology through that large scale fab. But over the last 15 years, it has been amazing how we've been able to push down the bit size in magnetic and other forms of memory.
So now that we've talked a little bit about some of the key discoveries that have advanced science and technology, could you talk a little more about how you have been involved in the NNI?
The first project I was involved in was at the University of Virginia, where we were hoping to get students introduced to scanning probe technique through a grant that was called We're Not in Kansas Anymore. And it brought scanning probe microscopy into the undergraduate lab so that the students themselves could have the experience of seeing materials probe at the atomic scale. And it is an eye-opening event, and it leads you to think of materials in new ways. So that's what we wanted to introduce people to that as soon as we could. My most recent project is addressing this idea of self-limiting chemistry and trying to do it in a way that, again, what we're trying to do is be able to control our chemistry. And electrochemistry has usually been approached with a potentiostat. But I'm not an electrochemist, and so I was never taught how to use a potentiostat. So that can either be a great disadvantage or a great advantage. The great advantage So being a laser spectroscopist trying to do electrochemistry is that you come to it with a different perspective, which is that, maybe I can do this without a potentiostat. And now I'm trying to essentially use a syringe pump as a potentiostat. And we do that essentially by having developed an understanding of how the Nernst equation meets quantum confinement to develop self-limiting chemistry. And so now I take my perspective as somebody turning to electrochemistry from the outside and say, why use the conventional instrumentation when you could use something that I'm more familiar with? And that's how I've developed a process now to make porosilicon powders. And we're trying to expand that to other materials, whether it be molybdenum disulfide or silicon carbide, and we'll see whether we can develop methods of this self-limiting chemistry to make nanostructured materials beyond silicon.
Some people talk about how the NNI created an ecosystem, how in early days of nanotechnology, the pivotal pieces that came together were across disciplines and multidisciplinarity. It really created a unique ecosystem that wasn't there before. Can you share your observations?
Yeah, and certainly if you're going to attack a problem such as that drug delivery problem, this is not something you do in one group with one set of assays or one brilliant machine. You need to pass this around between different groups who have different expertise. And you need to facilitate the language of how they can talk to each other. You need access and intersection. You need some common areas. It's great if you can have materials passed around between labs, if you can get people talking about the same materials and what they're going to do with it. That's important. Sometimes the language barrier can be substantial if you're really going from biology to physics to chemistry. So there are ways in which you have to broaden your own expertise, but there are also ways that you have to learn to be able to hand things off and have other people express their expertise to move some of these projects along. Certainly, shared instrumentation can be very important to that access and intersection that's required for these, right? Not always an easy thing to be able to do this. You have to be able to travel. You have to see people, whether that's going across campus or going to another university. You can pass samples around between groups, but you need to pass people between groups as well.
Could you give us your insight toward the future? What do you think are some of the most significant challenges that nanotechnology might help to solve? Or where do you think key breakthroughs are still needed in nanoscience in order to address either known challenges or challenges to come?
For me, something that really interests me, something that I see as one of the greatest challenges, is the energy issue. With enough energy, you can even slow down time. That's what relativity tells us, right? So that if we can crack the energy problem, then everything else can be, as it were, derived from that. So I see things that impact on that will have a huge impact. And for me, I would see control of electron transfer as one of these key fundamental kind of things. And that's really broad. That's electrochemistry, that's photovoltaics, that's artificial photosynthesis. And that is related in many ways to this energy problem. Nanotechnology is going to be all over that. How we move our conceptions of electrochemistry, in a lot of ways, what we think of electrochemistry is very much from a continuum model. And we're trying now to make that more atomistic. We're trying to understand that on the nanoscale. How do we make good photocatalysts? How can we make an artificial photosynthetic system? How do we control photovoltaics for direct access to electricity from photons, right? So there are two very different sides to converting photons into useful things, whether you convert those into useful chemicals, solar fuels, as it were, or do you just turn it into warmth That's not a very high-grade form of energy, and so that's why we'd like to turn it into electricity as well. And then we can use it to power our lifestyles and diagnostics for medical treatment and everything else.
I want to thank you so much for taking the time to talk with us today, and want to give you an opportunity to share any closing thoughts that you might have with our listeners.
Well, thank you. This has been a lot of fun. I really enjoyed talking about this. And the thing I'd just like to sum it up with is never stop being amazed at the wonders of curiosity-driven research, and never stop teaching. It's what separates us from any other form of life, is how we pass things on. Talking and understanding and just developing a better conception of what's going on around us, it's what makes us human.
Thank you for joining us today for this story from the NNI. If you would like to learn more about nanotechnology, please visit www.nano.gov or email us at info@nnco.nano.gov. And of course, check back here for more stories.